All of you welcome in our next period. Extension of Hamilton's principle to non-holonomic system. A reasonably straightforward treatment of non-holonomic systems by variational principle is possible if the equation of constants are expressed as f alpha of, that is f alpha is a function of coordinates q1, q2, so on qn, comma q1 dot q2 dot so on qn dot equal to 0. Question 1. When this can be done, then constants are called semi-holonomic constants. Here alpha indicates that there may be more than one such equation. Let there are m equations in all, that is alpha equal to 1, 2 and so on up to m. One commonly occur in the form summation aik dqk summation over k plus and so on plus ait dt equal to 0. Equation 2. The varied paths or equivalently the displacements constructing the varied path should satisfy equation 2. The procedure for eliminating these extra virtual displacements is the method of Lagrange's undetermined multipliers. The method for eliminating the extra virtual displacements is given by Lagrange undetermined multipliers. If the equation 2 hold, then it is also true that summation lambda alpha f alpha equal to 0. Equation number 3. Hamilton's principle, that is variation of integration t1 to t2 L dt equal to 0, where L is the Lagrangian of the system, is assumed to hold this semi-holonomic system. By combining equations 3 and 4, we get variation of the integration t1 to t2 L plus summation lambda alpha f alpha dt equal to 0. The variation is performed with n delta qy and m lambda alpha for m plus n independent variables. Then we will see example of this method, that is the Lagrange's undetermined coefficients, undetermined multipliers. Consider a particle whose Lagrangian L is given by this equation 6, 1/2 m into x dot square plus y dot square plus z dot square minus v of xyz. This first one is the kinetic energy and v is the potential energy. Therefore, you know the Lagrangian of the system is given by n equal to T minus v, kinetic energy minus potential energy, subject to constant f of x dot y equal to x dot y dot plus ky equal to 0. The resulting equations of motion are given by mx2 dot plus lambda into y double dot plus lambda dot y dot plus del v by del x equal to 0. Second equation my double dot plus lambda x double dot minus k lambda plus lambda into x double dot. This double dot means double derivative of this x, d square x by d square dt square, d square x by d square y by here is x, therefore d square x by dt square plus del v by del y equal to 0. Third equation m into z double dot plus del v by del z equal to 0. And the equations of constant 2, this equation 2 implies that y dot x dot plus ky equal to 0. consider the Hamilton's principle in the another form as consider the Hamilton principle in the form, let the Hamilton's principle in the form del, that is variation of the integration L dt from t1 to t2, integration from t1 to t2 equal to variation of the integration t dt from t1 to t2 minus variation of the integration t1 to t2 u dt equal to 0. Which is the next equation 10. If the variation of the integral over the generalized potential is carried out, and so the principle takes the form, another form, also del variation of t dt from t1 to t2 equal to minus integration from t1 to t2 summation over k qk del qk dt. And the constant Hamilton's principle says that the difference in the time integral of kinetic energy between the two neighboring paths is equal to the negative of the line integral of the work done in the virtual displacement between the paths. Hence, Hamilton's principle says that the difference in the time integral, which is given by this time integral of the kinetic energy kinetic energy means T between the two neighboring paths, between the two neighboring paths is equal to the negative of the line integral, which is the right hand side integral of the work done. This is work done. Integral of the line integral of the work done in the virtual displacement displacements between the paths. And this is about the example of the Lagrange multiplier method.